And hi, welcome back. We'll continue where we left off. We were talking about some of the very high level overview of what the kOmega model is about and some of its variants, especially the hybrid with the kOmega SST model. That is a blend between the kOmega and the kepsilon model. And now we want to talk a little bit more about how turbulence viscosity is managed in the kOmega model and compare it to the kepsilon model. So I'll just do this here. Okay, so these are the closure terms using the Boussinesq relation. Okay, I think I'll use this, is a lot better. Yeah. So this is how we do the closure problem. So remember that when we do this Boussinesq relation, we have this we represent this closure model using this way. Remember, this is Einstein notation. I'm not going to go through Einstein notation again because I went through it before very extensively. And this is the Kronecker delta, which again, if I is not equals to j, that is 0. If I equals to j, then the value is 1. So that's Kronecker delta, and all of this is in Einstein notation. But what it's saying is that, okay, I have this Reynolds shear stress term. I've divided it by density, of course, and then you have the turbulence viscosity into some velocity gradient. Okay, strain rate. This is also called the strain rate. Okay, so yeah, and this turbulence viscosity is modeled like so. Mu t equals to, all right, some constant c mu k squared divided by epsilon. All right, this is the k epsilon. For reference, and oopsie, yeah, if you want to take a look at the k epsilon model here, you'll see that this is pretty much the same. Turbulence viscosity is modeled as mu t, this mu t here, equals to rho into c mu k squared over epsilon. So this is a dynamic viscosity, so you just multiply by the density, then you'll get the dynamic viscosity. I use kinematic viscosity because, yeah, I'm more like used to it. So yeah, and then how are the transport models of k and epsilon done? I'll just scroll back and do this. Okay, so where's the k? Yes, these are the two transport equations, okay, for k and epsilon. So these are the two transport equations. So in the whole place, k and epsilon will vary according to the what do you call that? According to the transport equation that you do, according and all the boundary conditions. So you probably put a wall function for these k and epsilon here. I mean, I didn't explain how we converted the velocity u into some boundary condition, but yeah, the fluid codes, CFD codes, they sort of do it for you. So I mean, on our part, we don't really have to know how it's done unless we want to do some custom function. But if you want to debug, it's useful, but honestly, we don't really need it. Okay, so this is the K model, the K transport equation. All right, so remember all these closure problems, these closure terms, they're substituted into the velocity terms, the Reynolds shear stress terms here, and this turbulence viscosity, which helps us to model all these Reynolds shear stress. Yeah, helps us to model these Reynolds shear stress. Okay, so the more viscosity, more turbulence viscosity you have, the more turbulence you have. So in this model, turbulence viscosity increases with turbulent kinetic energy, which is pretty yeah, I mean physically expected, and it decreases with the dissipation rate. So the more turbulent kinetic energy is being dissipated into heat, which is represented by this epsilon. This is the rate of dissipation of the turbulent kinetic energy. The more you have that, the less turbulent viscosity you have, because there's less turbulence. Okay, so this is what we use to model turbulence. And okay, there are some model constants here. Okay, you see the turbulence viscosity kind of pops up here again. And then you have sigma k, P and D, and sigma k, P and D are all, I think, stated above. Okay, all right, I didn't put it there. Never mind. Just to make it more complete, let's go to this. Okay, so sigma k is 1.0. Yeah, so you see there's a sigma k here. Sigma k is 1.0. Okay, sigma epsilon, which is the epsilon equivalent, sigma epsilon equals to what is this? 1.3. Okay, sigma epsilon equals to 1.3. What else? The P and D, we kind of discussed it before. These are the production and destruction terms. They were given by this. Okay, so this EIJ thing here, this represents the production and dissipation. Okay, so this is what EIJ is. I discussed that before, so I'm not going to go through that again. Okay, so this is the production rate. This is this P term, and the D term is, you know, yeah, the D term is term as rho times epsilon here. Okay, so the D term is rho times epsilon, and the P term here is actually this 2 mu EIJ thing. So that's just a recap. I will put this here. P equals to yeah, so what's P? If we take a look here, P is referring to this pk thing over here, which is actually mu t into s squared. Okay, where s squared equals to 2 times this rate of strain tensor kind of thing. So P, okay, so this one actually is divided through by viscosity. I mean divided through by density. So we don't do anything there. We will just say P is nu t, s squared equals to nu t. So in this context, okay, because this one is divided throughout by density, nu t equals to P equals to 2 nu t times Sij. This is the mean rate of strain tensor. I'm not going to go through what that is. You can take a look at the earlier videos if you want to know. Okay, and D equals to just epsilon. So this is the destruction term. So if you were to compare to this model here, I only consider this pk, which is the production of k, and this rho epsilon. Okay, of course I divided it through by I did not divide it through. We just have an equation that's the version that's divided through by density. Over here, it's all divided through by density, unlike here where you multiply the density in. So I divided it through by density so that the destruction term is just epsilon. The source term, sk here, that's just arbitrary for you to insert your own source of turbulent kinetic energy. It's pretty arbitrary, so just ignore. Pb, it's a buoyancy term, which for the purposes of this video, I also ignore. So what you're left with is this ym over here, okay? Which for all intents and purposes, I also ignore. We just do a very basic one. So we just have pk and rho e. So, or else it's a p and d here. P being this rate of strain tensor into the turbulence viscosity. So this is the production rate of turbulent kinetic energy. All right, and then this is the destruction rate, which is the dissipation rate here, which totally makes sense because that's what we want. All right, and in the epsilon equation, we have again C1e into e over k. Okay, so C1 into e over k, the production term, and then C2 e over k, the destruction term. So where you will see the C2 e, it's over here. This term I'm kind of trying to highlight but can't highlight. C2e rho epsilon square over k, that is the same as this term here, multiply into this. And the first term, C epsilon 1 into p, it's this term here. This term is the buoyancy term, and this term is your own source term, which again I will assume is 0. I'll ignore for the purposes of this video. It's just a revision, not going to do too much. So in the standard model, C1e is 1.44, or CE1, C epsilon 1, var epsilon 1 equals to, all right, 1.44, and C2, C var epsilon 2, C var epsilon 2 equals to 1.92. These are empirical constants, you don't have to worry too much, but these are just some typical values for you, and it's just to help you to understand where all these things are coming from. Okay, so now that we have this as a reference, we can ask, what about the kOmega model? All right, so what we need to do is this. Okay, we will just try and adopt this to the kOmega model. K model, okay. Before I do that, the closure model is the same. And we'll still have this C mu into k over epsilon. There, closure model and viscosity model are the same. Okay, so this is the closure model, and then viscosity model is as such. It's the same thing. So okay, before I forget, C mu equals to 0.9 or 0.09. C mu equals to 0.09, and that is shown here. C mu equals 0.09 in the k epsilon model. Okay, in the kOmega model, we have omega equivalent to epsilon divided by k. So this is some specific dissipation rate, otherwise known as the turbulence frequency. Some people call it the turbulence frequency. All right. Yeah. So this is a turbulence, sometimes called turbulence frequency. There's omega has the units of frequency because this is the rate of dissipation per second, and this is the rate of dissipation of kinetic energy per second, and this is in units of kinetic energy. So this is actually per second. Okay, so Sometimes they call it the turbulent frequency. Alright, so anyway, we get back, we look at this Wilcox kOmega model from CFD Online. So these are some useful resources. And nu t, as shown here, nu t equals to k over omega. Okay, so from the website, the CFD Online website, nu t equals to k divided by omega, where in this case omega equals to beta. It is some constant times omega then k. So this is the special way of putting this epsilon here. Alright, okay, so in this case, this is one variant of the kOmega model. Omega equals to, so okay, rather I just write it down, epsilon equals to beta star omega k. Okay, what is beta star? Beta star is 9 over 100 or 0.09. Yeah, so it's exactly the same, 0.09. Alright, so if I make omega the subject here, omega equals to epsilon divided by beta star and then k, beta star and k. So omega is that, and if we just substitute this into the model here, we will get the following. So we just substitute in omega, and then we'll get beta star square, or beta star, no square there, beta star k square divided by epsilon. So this is 0.09 times k square divided by epsilon. So you can see that the viscosity model is exactly the same in terms of numerics. Now I know there will be some confusion here because the omega we define here is defined as some epsilon over k. That is what this book uses here. And for this website, omega is defined differently here, which kind of gives it a little bit of a headache. But if we kind of just put this omega definition of omega into this equation, I'm pretty sure a lot of the constants will just cancel out. Okay, and then we'll get a very similar expression to what we have here. Okay, but that is for the topic of the next video. Okay, so remember, I'll just highlight here. This is textbook definition. This is from the CFD website. Okay, so maybe I would use omega star to represent this, because I don't want to do have it confusing you or something like that. So this is from the textbook. Okay, this is our standard definition of omega. This is what they use in the website. Okay, we can do some reconciliation later on, but for now we will just use this omega star definition. Then we'll see how both of them are related to each other. So thanks for watching. I'll see you guys again next time. Goodbye.